Your boy is a co-host.
Am I a co-host too or no?
No, I think I didn't tell him about you. I don't think I assumed you were going with me to the Ashkan meeting.
My
My
bad.
bad.
It's okay. Well, technically, if I'm not a co-host, I shouldn't be able to. Uh, I am a co-host.
Oh, all right,
You
cool.
can just open the chat and you can see whether you're a co-host. Oh
I am
shit.
indeed a co-host. All right, cool.
Crap. Where's my Zoom thing? Oh, give me 1 second. All right. So let me start recording.
I am
Okay.
currently recording as well.
All right. So,
Um,
you want us to go first again? Does that work for you?
yeah, I guess the same order we did last time, which was on the spreadsheet, right? So it
Yeah.
should be Vincent, Basel, and
Uh,
Saul.
yeah.
Yeah. Can you guys hear me
All right.
well?
Yep.
Yeah, I can
Yeah.
hear you,
All right,
man.
cool.
Everything's good. Okay. Let me start sharing screen. Screen one. Share. Everyone can see that okay?
Yes.
Yep.
Okay. Awesome. Let me just move this thing slightly to the side. Okay. So this is Improving Swarm Technology through Edge Learning by myself, Vincent Cavalieri.
Total Taurus.
And I'm best of the
All right. In our presentation, we wanted to cover several topics, which included what defines swarms, the current pros and cons, how edge learning can improve upon already powerful technology, and with that technology, where's it going to take us? So the first thing is what defines a swarm? So there was 4 categories in which I saw define a swarm. The first thing is that they had to be fully autonomous by themselves, which makes sense. This is like the whole point of it. So each individual had to be autonomous and only have slight guidance through GPS and stuff like that. The second thing was the size of the group, which is the most obvious trait. The interesting part is what actually defines a swarm is that from what I saw, the accepted minimum is between 10 and 20 units inside of a group considers it a swarm. But as for the maximum, there is no true maximum. When I went to go do my research and just try to figure out what the largest one is, the largest swarm that was assembled according to the Guinness Book of World Records was the light show in Shanghai, which had 3,281 drones working together. So in a swarm. So as for the cap, there really is none. The next 2 traits, on the other hand, were a little bit less apparent. The first of those 2 traits were that they had to be individually unable to carry out the task, which sounds a little bit silly, but the best way to compare this to is ants, which they like to compare everything in swarms to ants. But basically, if like there was a bigger piece of prey, one ant could not pick it up by itself, and multiple ants had to carry it. And that's kind of the idea of what they define as a swarm, is that one particular unit couldn't carry out the task all by itself. It was kind of a little gray area, but it was also in relativity to the job. And then the last thing is that they actually had to have limited sensing and communication capabilities. And what I mean by this is, besides having like coordinates of where to go to, the swarm itself really only communicated with itself, and the coordination is within the group itself. It's kind of a hive mind type of mentality. And because they're autonomous, they're really not supposed to have any outside help to guide them. So with that being said, the next thing that we went into is the types of swarms. There's 2 types of swarms, which are homogeneous drones, which are what you're familiar with the light show and stuff like that, where they all work together to do the exact same task. They all have the exact same functionality. They just use greater numbers in order to complete their task. Where the next thing is heterogeneous, where different drones have different roles and in which they do different tasks. So like these particular ones you see on the right, the one that's on the far right that looks like a quadcopter with a tower on it is actually a I unit. And on the left of that, there is a arm unit with 3 feet units. The particular task that I saw this thing do was it had to go retrieve a book. using the I unit found the book. The arm unit went and called for the feet units. They combined together like a megazord, and they crawled to their destination. And then using the arm robot, it was able to climb onto the bookshelf and grab the book. So that's kind of a heterogeneous type of system. So now the question is, what about swarms makes them preferable in comparison to other approaches? So, and this broke down to 3 categories: robustness, flexibility, and scalability. The robustness is due to the fact that there's so much redundancy that the chances of failure were much lower because there's more than one unit trying to achieve the same task. So with that being said, it had a higher success rate. The second part is the flexibility. Because there was multiple units inside of a group, instead of having one unit that has like extra sensors or something like that in order to find something, they would use multiple drones in order to have a broader perspective of a particular problem and be able to work together in order to overcome their task. Now, the last trait is the scalability. As I said, swarms are groups. The thing is that the higher number of units that are in the group, the greater the other 2 traits are by an exponential amount. Because the more that they can see, the more that they can problem solve. Just basically the more points of view give them a better perspective into how to solve a job. So like as for example, if it was a search and rescue type of situation, the more drones they have, the more ground they can cover, the more places they can look. And it just allows them to complete the task in a much better fashion. So with those 3 being like kind of the pros to why you would choose swarms, I'm going to hand this off to Basal, who's going to actually start the cons.
Yeah, thanks. So, so we talked about some pros with swarms. So what are some cons? Where are they not really useful? Why would we not use swarms? Obviously, first, the increased cost of operation. Obviously, when you add in more more drones into a swarm, obviously you're going to have greater costs. So you have to weigh your options and see whether that increased cost is outweighs the cons that you would have. Another one is security. If they're working in sync, if one were to be compromised or get hacked or anything, then it puts them all at risk. Another issue is communication. This is communication between the drones in the swarm, but also when you introduce them to other drones, they also have to be able to communicate with them and make sure that they can still complete their task without affecting anything else, and also like interacting with their environment while communicating with other drones. Redundancy can be a pro where it increases the higher success rate, but it can also be a con, which is linked with the cost of operation. You need to find like a sweet spot with the number of drones that you use. So you're not just adding them in and they're kind of being redundant and they're not like, and they're doing some of the overlapping tasks and stuff to where you're just increasing the cost with no real output. And then also you have to put in some faith in machine learning. There's no human operation to fall back on. So you just want everything you have to make sure that everything like works as it should, because there's no really fallback option. Thank you. So yeah, so the architecture of a typical machine learning in normal operation is that there's a device and it would communicate and send prediction requests to a cloud-based API system. And this would require a network connection. And then the cloud-based API system would send back a response to the device over the internet or over a network. So that's how regular ordinary machine learning is used to queue. And then, so, why can't we use this with drones and swarms? Some drawbacks is that for small data transfers, like small snippets of text, small snippets of code, the regular typical machine learning is totally sufficient. But when you're sending bigger pieces of data, which is like higher quality photos, higher quality videos, things like that, the entire process kind of breaks down and there's like a lot of latency that you would have over communicating over this network. And especially in remote areas where the network coverage can be pretty low or even no network at all, then obviously communicating between the cloud-based API and regular machine learning is just not viable. Thank you. So this is where edge learning comes in and edge AI. So the architecture of this with edge learning, the entire model is built into the device. In this case, it would be each specific drone. So whereas in typical machine learning, each drone would have to communicate with the API on the cloud and then wait for a response back over the internet. They would have built-in AI algorithms within each device. So then they wouldn't have to communicate. They wouldn't need an internet connection or anything like that. You'd have reduced latency because you're not waiting for a response back and everything like that. Q. So some advantages tying this back to drones and swarms. Drones and drone swarms, they're frequently operated in more remote areas. That's, where you wouldn't want to put humans. So obviously a lot of these areas are, they won't have good network connection. They might not have any internet. So edge machine learning is very, very useful in this scenario because there's no latency involved. Also, you're not going to lose battery life streaming back photos and videos or like maps of the terrain or the area. So the drones will end up having better battery life, which is good for having longer tasks and longer missions. And then also there are costs, of course, related to data communication between the devices and the cloud. So that cost is basically essentially all cut out when you have edge machine learning. And I'm going to pass it off to Saul here.
All right. As mentioned before, like Belso said, one of the main problems with AIs is that they're not able to process that much, well, not AIs, but swarms they're not able to process that much information. But with machine learning, they're able to process information at real time and process it much faster. One of the benefits that I was finding is that something that we don't take into account is that there's so much data out there, as you can see on the graph below, that sometimes instead of running through all that data, we can just run out through the data that we really need, making devices with specific battery lives so viable. And this is why it's important to have a good machine learning implementation, and that's one of the benefits that swarms could benefit from having machine learning. Next Q. Another benefit of machine learning with AIs is security. So there's two types of drones in the way that they work. There's centralized and there's decentralized. Centralized is there's one unit in control of all the rest of the units. And even though it's helpful in certain situations, we have found that it's caused a lot of more damage than good. Because if that one centralized unit, the leader of all the swarms, breaks, then they all get destroyed. But with machine learning, they're able to process their own information, process it by themselves, and in that way they can be a decentralized architect, meaning that if one breaks down, if one gets damaged or one gets hacked, then the rest of the drones can operate by themselves and still complete the mission without having to rely on that one leader unit. Another thing with machine learning is machine learning can implement ABC algorithms in an RR training, which is just algorithms that are used to find any anomalies in data or structures. So if somebody hacks one of the swarms, they're able to use the machine learning to see like, hey, there was an anomaly at this time. We should either shut it down or we should do something about it instead of letting it happen and maybe damaging the rest of the drones. Next Q, please. Something that we were looking into was current applications. Although the technology is very basic and it's not at its fullest, swarms are still implemented around the world. As Vincent has explained, they were used in Shanghai. They were also used in 2016, a couple years before, with Intel. Intel was able to like almost quadruple that in the following year, and they also won a Guinness World Record. It wasn't until China came out with their Chinese company and was able to do even double that and even quadruple that. But they're not just made for entertainment purposes. They're also made for tracking and monitoring certain missions, such as in the military, where we discussed in our last presentation, where we talked about how they're used to monitor and track certain individuals or certain roads or areas. But they're also used in other types of versions of monitoring and tracking, such in an environmental field, where they will track natural disasters such as forest fires or floods. And with special help of special sensors, they're able to track the perimeter of a forest fire or the flood and see where it's going to be going and where it's not going to be going. And that way they can talk to the first responders or firefighters and get the best help to save people or to possibly mitigate the damages that these natural disasters are causing. And one of the last fields that they're also very useful in is agriculture. A lot of farmers are trying to implement swarms all around, and some of them are successful in it, where they're able to track crops that are that have water shortages or insects or rodents that are killing them. And where having one single drone or having a bunch of people just going around trying to find out all these areas, swarms can just cover a large amount of area in little time and process that information right away in just a few seconds, if not a few minutes, making farmers' lives much easier and much better. Next cue. With the current applications, a lot of research and a lot of organizations have been trying to push the limitations of swarms and try and see where the future will lead. One of the biggest things that the military is doing, I know that we talked about surveillance and monitoring, but they're also trying to like monitor and track other drones. As drones are becoming more accessible to the public and more consumers, there's a rise for dangerous drones to appear more often. And so the military is trying to have swarms that find and track enemy drones and possibly disable them. There's a lot of research that we were looking at where they're trying to embed FREs and RFs, radio signal frequencies, that just jam the signal from enemy drones, and GPS jammers where they just disable all the GPS tracking on the counter drone, on an enemy drone, and that way they're not able to find their way or find their position. A notable field that they're also trying to push is transportation. Amazon was able to deliver a package back in 2016, and the FAA has approved autonomous drone in urban use. But the problem is that, especially with Amazon, is that a single drone isn't able to lift large packages or bring them through large areas. So there's a lot of research right now where drones are able to pick up packages and fly them all around in 3 axes. And that's one of the future applications that we have seen. And the last one where swarms seem to be the most beneficial is in network. They're almost like satellites or your cell towers that you see every day. They're being used to transfer signals back and forth so that the way they can extend the network, such as 5G, 4G. Actually, the military is already working on that. They call the program Hotspot, which kind of seems like a simple name for them because we already know what Hotspot is and how we use it. But essentially, it's just transferring signal from drone to drone in a swarm. So that way they can get 5G and 4G across to remote troops around areas where networks aren't available or information can't be gathered. Next cue, please. Our concluding remarks. So we talked about the drones and what swarms are and how we define swarms. And we also talked about machine learning and how machine learning is the future for swarms. One of the biggest limitations that we talked about was how swarms aren't able to do much by themselves or with the help of people, because humans can only do so much. But with machine learning, especially edge machine learning, which is much faster, much better, swarms can do what the future applications we just talked about. And that's really where we're at the given time. Next cue, please. We divided our work distribution Vincent did slides 1 through 5. Bazal did 6 and 10, and I did 11 and 15. And then right there we have the topics that we worked on. Next cue, please. And then these are all our reference for all information that we gathered throughout the whole PowerPoint. Thank you for your time.
All right, any questions?
I have a question, if that's okay, really quick.
Yeah, all the questions.
It's for Saul. I missed if when you were talking about natural like drone swarms patrolling for natural disasters, like forest fires and floods and stuff like that. Did you say that was a current technology, or is that something that's in the near future?
So it's somewhat current and somewhat in the future. Some of the like tracking and being able to like find out like where it's going to be going is still a little bit in the future because of the algorithms, the limitation on algorithms.
Mhm.
But tracking in real time and visualizing where the weather is at, or where the flood is going, or I mean where the flood is at, or where the forest is at, forest fire, I mean, that is right now current.
That's awesome. Cool. Thank you.
I also
Question.
had a question. I believe you mentioned edge learning. And you said it was kind of like built into the drones, but is that like a real-time decision kind of situation that you said that they didn't have to send it back to any type of server?
Yeah, so that's like I'll take this one. So yeah, it's like in real time. So with regular machine learning, you'd have to send and wait for a response from like an API that's based in the cloud. But with edge machine learning, everything is done on the device, or the edge of the network is the device. So yeah, the algorithms are made and the decisions and the predictions and stuff are all made like from the device. So it doesn't have to wait from a response, doesn't need a network connection or anything like that.
Okay.
I have a question. I think it's for Vincent.
Okay.
What's the most beneficial characteristic that you mentioned for Swarm out of the three? I think it was like robustness and
It was robustness,
Okay.
flexibility, and then scalability. So they're all important characteristics that just come with the territory. The scalability, I think, is one of the biggest factors, only for the reason is that as you increase the numbers, the other two traits exponentially increase with it. So like if you're trying to complete a task, having 20 drones to do something in comparison to 10 is going to give you a higher chance of success, because that helps with the robustness and make sure that it makes it easier for the mission to be complete, covers higher amounts of area. And then the flexibility is also based off of the scalability, because like as for example, if let's say they were trying to find their way into a building, right? If you had 2 drones, you could look at 2 sides at a time. If you had 4 drones, you could look at all 4 sides at the same exact time. So the more drones you have, the more perspective you have. So it makes it easier for problem solving, because basically it's kind of like solving a Rubik's Cube. It's kind of hard to solve only using one side unless you memorize it, but that's besides the point. But if you can see all 6 sides at the same time, it makes it a lot easier. So that's kind of the idea, is that as you increase the numbers that are inside of the group with the swarms, it also increases the robustness and the flexibility that go with it. So in my personal opinion, the scalability, being that we're talking about swarms and it's a whole thing is about groups, given there was traits that you have to watch out for, because having too many things for one particular job might be overkill. You know, there is a sweet spot, but scalability, I feel like, is the biggest, most important pro characteristic, because it helps the other two. So
that's perfect. Thank you.
I actually have a question. The biggest limitation, do you think it's like scalability or security?
the limitation to swarms.
Yeah.
Well, if you're talking about the numbers, resources, because
Yeah.
obviously you can only make so many. The limitations right now is, I don't know. I think it depends on what part of it you look at. So the security is a big issue, just for the reason is that when you're sending anything wireless, it's not too hard to intercept those signals. That's why when I was talking about the communications part and what defines a swarm, that the communication roughly, give or take, stays within the swarm itself. That's to try to limit it. Now, the thing is the reason we were talking about how we believe that edge learning could help a significant amount is because how edge learning works in comparison to cloud learning, which we learned is cloud learning takes all this raw information, sends it back to the cloud, and the cloud sends out a new training model. Now, and the differences is edge learning, they basically create training data inside each unit and then send the training data eventually back to the cloud whenever they hook up back to the server. But they are creating their own solutions. Basically, they're not waiting for someone to give them a solution. So I feel like the biggest limitations on swarms is this: it really depends on the situation. If it's distance, it's battery life. If it's an urban situation or something where you have to go into an enemy territory, for that matter, hacking would be an issue, which I would believe machine learning would be a little bit of a good solution for it. So it really depends on application to where the weakness is going to really show.
Okay.
I just
Anything
had
else?
one thing. So pretty interesting that heterogeneous swarm that was shown at the beginning of the slideshow. I was just wondering, could you guys like put a link in the chat or something so like I could look more into it?
Yeah, I can, but I'm going to tell you right now, it's real creepy.
Okay.
So it's funny because the swarmanoid, which is what it's called, is I found it actually like last night, just going through like what a heterogeneous like different examples were, and that was like the first one that popped up.
Oh yeah.
And it's actually old. Like that's a thing all the way back from 2011. So 10
Oh,
years
wow.
prior, like can you imagine how much further we got?
Yeah.
Well, I think I actually still technically have it up. I'll look at my history real quick.
All
But
right, cool.
yeah, they play this creepy horror 8-bit music in the background. I'm not a big fan of. So, but yeah, I'll put the link in the description for you.
All right, cool. Thank you.
Not a problem. All right.
All right. Any more questions? Going once.
All right. Any other questions?
Sold to no one. Awesome. All right. So the next group is the one
That
that's
is
not
us.
mine. Yeah.
Yep.
Do you guys have screen sharing capabilities?
Yeah.
Okay. You are more than welcome to share your screen whenever.
Did your last teammate show up?
Yeah.
Yeah, I'm here.
Okay.
Sorry.
No, everything's good. I remember they saying that was a problem, so I just want to double check.
Alrighty. Yeah. Sorry if I cut in and out. It's I'm on the school Wi-Fi, which is why it took me so long to come in. So I'm sorry about that.
It'd be like that, man. Don't worry.
All right.
Okay. Sorry. Give me just 1 second. Okay. Okay, so hello everybody again. Just like last time, I'm James, and with me are Beden and Berkai. And if you remember, which I don't blame you if you don't, our topic is on Spot, the Boston Dynamics robot dog, and how it can be enhanced in order for it to be able to fulfill, a wider array of tasks. Basically, just making the design and functions of Spot better all around. But let me just give you a brief recap of Spot. You can go to the next one. If you remember, Spot is an autonomous robot that can maneuver difficult terrain and can make real-time decisions based on its environment. It's made possible with its 5 internally mounted cameras, and these cameras allow for a 360-degree view of its environment. As you said before, Spot doesn't come without some limitations, which are the battery life, general safety concerns, and limited ease of use, just to name a couple. And with that being said, the general structure of our presentation is going to involve dissection of several reports related to these issues with a potential solution that could be implemented into Spot design. If I could summarize the problem, it would be that if you can go to the next slide. Spot isn't able to plan and perform high-level tasks because it's beyond its current designed purpose, which is a real shame. And that's what we hope that, if you can, go to the next slide. By adding extensions, sensors, upgrading its processors, and changing the design of its chassis, hope I'm pronouncing that right, we can ensure that it can perform more than its current software and hardware allows it to. There is always a demand for work that Spot can adapt. There is always demand for work that Spot can adapt to inside of an ever-changing work environment. If you can go to the next slide. For this outcome to be accomplished, we first must go over one of the most important aspects of any robot design, which is safety. Since the goal for Spot is for it to be able to work side by side with humans, it's extremely disappointing that Boston Dynamics has very strict safety procedures when it comes to handling Spot. I know that sounds a little weird, but let me explain. So Boston Dynamics has been adamant in informing their users that they should remain at least 2 meters away from Spot while it's in operation. As you can imagine, this is going to be a problem when it comes to the side-by-side work with humans that I just spoke about. Furthermore, a report by Avsari Keshirme, I'm fairly bad with names and pronunciations today, sorry, which focused on a 4-legged robot being used in construction monitoring, noted that limitations like these can fundamentally exclude Spot from working in many places, especially in a construction zone setting where Spot can be of extreme use. I mean, Spot would either have to work, Spot would either have to work outside of human hours or be isolated to its own path, independently away from everybody else. The main problem with Spot when it comes to safety can be traced back to its design. Spot has many pinch points all around its body and can cause serious damage to an unprotected hand. Straps are attached to the body so that you could set it up with little risk, but this does very little to fix the actual problem. Spot also has a total of 12 strong motors, each on each leg. That can also be a big detriment when it comes to safety. If you can go to the next slide. Thankfully, this is an easy solution. Sorry, next slide also. Okay. Thankfully, this is an easy solution. You can just cover up these motors and pitch points with the same material that Spot's main body is composed of. This would greatly improve Spot safety and allow for safer and easier handling. It would also not be a big detriment to its overall maneuverability, since the materials can be made flexible enough for Spot to carry on its duties. Now, workplace safety isn't the only concern. We have to think about the bigger picture. We have to think about potential issues that Spot can run into while in public areas, such as in a report for example, a report which focused on autonomous robots interacting with shoppers. Although the overall experiment went well with shoppers saying that they enjoyed their shopping experience, the tested robot experienced some glaring difficulties, such as its single-minded determination to finish a given task, which if you think about it, can be very dangerous depending on the situation, especially in a public setting. This is exacerbated by the fact that Boston Dynamics safety manual claims that Spot should be given the right of way when it's in motion, even when it's being controlled, via the controller that it comes with. We'll expand a little later on this, but simple, voice commands can be implemented into Spot in order to provide new commands on the spot, pun intended. But anyways, that's it for me. I'm going to hand it over to Berkai.
Hello, everyone. My name is Berkai, and I'll be discussing what is required to improve Spot and what that will do in enhancing its capabilities. While Spot can be improved with exterior advancements such as steel limbs, which can help lift heavier loads, the software advancements are what will bring a positive change into our everyday lives. Spot with an arm extension could help a majority of the population see a doctor when there is a disease outbreak such as COVID. The process would be so much faster letting Spot take over the application process and speaking to your doctor face-to-face at a time where there are many trying to see their doctor. Voice commands can make it more convenient for households to operate Spot, letting it know what to do. Commands we use on our phones, such as asking what the temperature is outside, can easily be implemented. Spot has many capabilities of which can be improved. It can already move around obstacles efficiently and pick up smaller items. Although the addition of new hardware and software, it is expected of Spot to perform for longer periods of time, pick up heavier objects, and have the ability to comprehend whatever you ask of it. With a multitasking machine like Spot, it should allow for many lines of work to be easier in terms of the toll it puts onto a person. Most importantly, for the widespread use of Spot to occur, humans need to accept that this machine will be able to do the work that they do. Transitioning into how Spot can take over a human's line of work, we know that humans are tasked with dangerous jobs. Farm work can be considered dangerous for the chemical-related injuries that come along with applying pesticides. 11,000 farmers die yearly from accidental pesticides poisoning, and Spot is more than capable, with minor adjustments to its software, to spread the pesticides on the crops itself. Overall, Spot can be at and enter zones where it'd be preferred for humans not to. When humans are asleep, instead of having one human patrolling an oil rig, we could have Spot patrolling 24/7 to alert the humans if something goes wrong. If an oil rig were to catch on fire, people would need to evacuate, while Spot can stay back and alert the humans what has gone wrong by using its sensors. Voice control technology has been introduced into our lives in some way. And while Spot needs a defining way at being controlled, the addition of voice control would do just that. Right now, you can make Spot function with the use of a controller, which is one more thing you would have to carry along. The Xiaomi CyberDog already has voice commands implemented, of which you can command it to do certain tasks, making it more convenient for human use. Spot can easily incorporate voice command technology, as even the smallest devices can make use of it. On rough surfaces, the use of Spot's limbs would be deemed the best way to move around. Although the addition of interchangeable wheels when on smoother surfaces would dramatically speed up Spot's movement. Adding onto Spot's ability to move faster, incorporating the ability to go onto its charging station and self-charge would mean that Spot can not only move faster, but it can do it for as long as it is functional. Now I'm moving on to my friend, Beden.
What's up, guys? I'll be discussing battery efficiency. So battery duration and control have not been a topic that is concentrated on in refining autonomous robots. More focus has been placed upon chips, cameras, and sensors, which are steps to allow for a non-error prone robot. In Spot's current form, it can sustain itself for 90 minutes at a runtime and 180 minutes on standby. This can't be sustainable for scenarios utilizing Spot. One standard solution for autonomous robots is the concept of self-charging. This works by setting a battery threshold, and once the battery drains to exceed it, the robot will redirect itself to a location where it can charge itself. This solves the common problem of low battery duration, but at what cost? So the main problem is that with thresholds, the robot won't take into consideration the value of the task at hand, and sometimes it won't even be able to charge itself due to the distance based on the location it's in. A proposed solution is to incorporate a risk gain assessment, which utilizes probability density functions to predict a favorable compromise between risk and gain. And in this scenario, gain is like the level of mission accomplishment. Just for illustrative purposes, this figure on the right shows a hypothetical profile of increase of risk and gain against time. The use of battery thresholds does not attempt to redirect the robot to the station at a time that maximizes the gap between gain and risk. The assessment uses probability density functions to incorporate factors of operating time, battery capacity, and the time it takes to redirect and charge using a risk gain parameter. Though this does sound like a neat way for threshold charging adaptivity, not all robots will work accustomed to a universal risk assessment strategy in evaluating the risk of battery drainage, since robots don't operate with the same Not all robots operate with the same set of technology. Therefore, this methodology still requires refinement. Next slide. So moving on, supercapacitors are an electrical storage device which can be recharged extremely quickly and release a large amount of power. These devices have the capability to transfer electrical energy to areas that require high surges of power in short notice. Supercapacitors can preserve batteries from high peak currents, which result in the deterioration of shelf life due to the device's property to instantaneously discharge at these currents. Not only does this preserve battery life, but it reduces the overall cost if the price of replacing batteries exceed the cost of just adding a few supercapacitors. Unfortunately, there are downsides to this, as supercapacitors could hurt the longevity within electrical devices. Some other problems are that they can't store the same amount of energy that lithium-ion batteries can, even though they do compensate with high power, dense charging speeds. Another problem is supercapacitors have a high self-discharge rate compared to lithium-ion batteries, and self-discharge causes a decrease in shelf life of battery due to its gradual voltage loss through each charge. A resolution to these downsides is to incorporate a hybrid battery supercapacitor that takes the best of both worlds of a supercapacitor and a lithium-ion battery. This consists of a two-phase power management plan that uses the high power density of a supercapacitor and high energy density of a lithium battery. As shown on the figure on the right, this power plan consists of a two-source structure where the lithium-ion battery supplies direct current for power need applications, while the supercapacitor supplies instantaneous high current and attains energy recuperation. Essentially, this plan allows a lithium battery to provide enough power for a mobile robot to work at conservative conditions and speeds, acting as a central power source, while supercapacitors provide peak currents and store the maximum levels of energy when the robot is braking or going downhill. These hybrid power systems have been implemented into a few mobile robots already for experimentation and have resulted in extended battery life, while also performing tasks of heavy load. A similar implementation of a hybrid power system between a supercapacitor and a lithium-ion battery can greatly serve to optimize Spot's energy effectively and increase its longevity on its working hours and battery duration. Next slide. Moving on, a defining trait of a robot is its ability to use sensing perception. Spot contains 5 sets of cameras, 2 in the front, 2 on the sides, and 2 on its rear. Each camera sees in stereo vision, and along with gyroscopes and sensors inside. All of this is feeding information to the computers at all times. And it's telling it how to control the motors and keep it balanced, Spot balanced. With these devices installed, it is capable of getting a good sense of its environment. However, Spot, it's still a robot at the end of the day and not perfect, especially with its sensing capabilities. Spot uses its cameras and sensors to build a 3D model around it in real time. This allows Spot features such as obstacle avoidance and ground height detection. One situational awareness area that Spot definitely needs improvement on is object detection, because it has trouble in some cases telling what objects are solid versus not solid. One proposed solution to optimize this is to incorporate a refined object detection system. A proposed method is to implement fast object detection from algorithms such as single-shot convolution neural networks, which split detection and task for localization. You can even implement them into generic cameras. This object detection system has been integrated into Spot's GPU, and has been found that the robot doesn't have major issues with detection and localization of physical objects, but has problems with non-physical ones, such as, for example, Wi-Fi or gas. The robot couldn't reliably localize a Wi-Fi signal until it drove right past it. Also, the robot couldn't localize the target gas, for example, of CO2, especially when there were different levels of gas concentration. Therefore, Spot had trouble detecting the levels of gas in a certain area. Though it is not fully optimized right now, this expansion of this methodology can help increase the opportunities for spot sensing capability. It hopes to allow exploration in unknown or hazardous environments. Next slide. So to summarize everything, autonomous robots are ubiquitous in this era. And the premise of our topic was to explore the capabilities and qualities of Spot and to point out what adjustments can be made in order to further our exploration and work endeavors. Here are sources. Thank you guys.
Is there any questions?
I got one. Quick question about the supercapacitor. Why does it hurt the electronics?
Why does it hurt electronics, you said?
Yeah, it was like the first point you made when you were talking about the solution being a supercapacitor. You said that it was going to hurt either the hardware or something inside of it.
I said it was going to hurt their longevity because they can't store the same amount of energy that like like the common lithium ion battery could.
I gotcha. So it's just like almost too much.
Yeah.
Um,
So while a supercapacitor would improve the battery life of Spot, and it does need improving, it would damage the overall structure of it itself.
I gotcha. So
It's
yeah,
mostly from the self-discharge that that comes with supercapacitors. That's like the main issue.
okay. Yeah, I was just curious about that. Thank you.
Do you think it's possible to add a bigger battery, or do you think that would limit the mobility too much?
Bigger
Um,
battery, just like a standard one, you mean?
Yeah,
Yeah. I remember correctly. Didn't you guys say there was an extended battery, but it didn't extend by all that much or something like that?
Yeah, I mean, there is an extended battery. It basically adds like 30 minutes to it. And it charges a little bit faster. It's not that much bigger than the original one. So if there was a way to basically, because Ben was talking about kind of mixing the supercapacitor and making the best of both worlds battery. So if there was a way to kind of make a battery like that and then put it inside of a Spot, I think that'd be the best outcome. But making it like a bigger battery, since I don't want to say it'll mess up its maneuverability, because it can store some payloads on top, which are a little bit on the heavier side. That's kind of not the proposed, that's not like the best of both worlds that you would want.
yeah, okay.
Yeah.
I had a question on the capacitor. Like, will the capacitor be already full with the energy, and then once you use it up, that's it? You gotta like replace it, or is it something that recharges and then keeps working in tangent with the lithium-ion battery?
Sorry, can you repeat that?
Like because I was doing like a project too with supercapacitors on cars that they would every time they would add like an extra, it would be like a hybrid for like lithium-ion battery and a supercapacitor or a capacitor. And what we figured out is that we could recharge the capacitor and just add extra energy or extra speed to the car. But you
Right.
know, the Spot with the the supercapacitor, I know it stores energy and it helps out with the lithium-ion battery, but does it recharge, or is it something that is like a one-time thing?
It does recharge, however, like I mentioned, it has like, because of its discharge, it causes voltage loss through each charge.
Okay, makes sense.
It basically acts like a battery. It runs out over time.
Okay.
Yep.
Okay, makes sense.
Any more questions?
Just one more off one. So there's another company making something similar to Spot. I think Cameron spoke of it. Is
Is it
Cyberdog
Xiaomi?
or something?
The CyberDog?
Yeah.
Is that the Xiaomi one?
Yeah.
Yeah. I'm about to say, how far are they with their technology? Do you think they're further than Spot or more behind in technology than Spot? Because it seems like it had better technology for some things, but I don't know if that was the only better thing it had.
It does have
Well,
some things that are better, such as the voice control technology that Spot doesn't have yet. With
Hmm.
Spot, you would have to use a controller, and with the Xiaomi CyberDog, you could use voice commands basically. You could tell it what to do, where to go, and what task you want it to accomplish.
One more thing. Yeah, let me add on to that. The Xiaomi dog, it doesn't have ground height detection, so it can't even like move upstairs.
Oh, okay. Yeah,
Yeah,
well,
it
that's a big defining factor.
With movement capabilities, it is much far behind. The Xiaomi CyberDog, for example, is worth $7,500, and the Spot the robot dog is worth around 10 times the price at 75,000.
75,000.
Well,
yeah,
damn.
the Xiaomi looks a little more advanced because it's a lot easier to
It's more
kind of, because
user-friendly.
it already had the basis, you know what I mean, of autonomous role, like for like Spot basically. You know what I don't know if I'm trying to say that right. The basis
Yeah.
was already there, so they kind of knew what to implement and not what to
I
implement.
gotcha. Yeah, I was just curious because that was the first time hearing about that company. So I was just wondering, like, if there's any competitors out there that were moving more forward in the field than they were.
It does have its advantages. It's faster, it's lighter, and has better battery.
Hmm. I gotcha. Cool. Thank you.
Any other questions?
Alrighty. Thank you for listening. That's been our
Thank
presentation.
you very much, guys. The next group can start setting up.
All right, I believe that is time for us, y'all. I will share my screen. Berkai, I think you need to stop sharing your screen in order for me
Not
to
sure how
share.
to do it.
It should be on your bar. If you hit space bar, sometimes the Zoom bar disappears. You can pop up and it'll say like share screen at the top. You can go and stop sharing from the top. It should be like a red button. I can't see the Zoom bar because it hides the Zoom bar from me, so I can't like point it for you.
Oh, right here. Yep. Is it stop sharing?
Awesome.
Yeah,
It did stop
figured
sharing.
it out.
Awesome. All right, I will share mine. I guess I'll just share the whole screen. Yeah, everyone can see my screen. I was just looking at the CyberDog. I didn't know it existed. So,
That's funny. I was just right there with you.
let me start that up. Okay, can see a slideshow, right?
Yep.
All right. Make sure I'm recording. I am recording. Okay.
Okay, so our presentation is going to be on techniques to improve people detection using machine learning. And my name is Jared Rimkos, and I'll be talking about edge detection.
My name is Christopher Rumpf. I will be speaking about the image processing.
My name's Cameron Nichols, and I will be talking about neural networks.
So people detection is become a very, very important technology recently. Not only important, but very popular as well. Popular in the sense that there are people doing casual engineering projects with people detection, and they can range from being as popular as that to being extremely important, like with crosswalks and detecting people in crosswalks with cameras, and even in very critical high risk cases like with autonomous cars, how autonomous cars need to detect people properly in order to make sure they're not hitting people when they're driving themselves. There's three main topics that we found in the whole techniques to improve, and those are image processing, neural networks, and edge detection. And the first one is image processing. This is what I personally researched about on this topic. Image processing refers specifically to, or generally rather, to operations performed on an image. And these operations can mean anything. It can mean changing the color, changing the look of it, changing how big it is, whatever. To process an image means to process an image. It can be done to increase the clarity of the image, extract information, or whatever. There are two fairly common groups that operations that can be performed on images group into. Those two can be either filtering or warping. Filtering refers to changing an image's display values, like the values of the pixels themselves when an image is shown on a screen, to manipulate the appearance of an image. Can refer to sharpening to increase the contrast of the edges, brightness to increase the brightness of the photo, color correction to change the colors or even correct them, etc. Warping specifically refers to changing or manipulating the position values in a pixel to change the physical shape of the image itself. That is commonly seen today with cropping, zooming, perspective changes, rotating pictures. And both filtering and warping both have their own purposes when it comes to processing images. Filtering can, filtering changes colors or changes the look of the image to make certain features stand out. Warping, zooming, or cropping can zoom in to highlight specific features rather than filtering the entire image.
So we'll be going over some neural networks, specifically convolutional neural networks. So what is a convolutional neural network? Well, the name itself comes from the mathematical linear operation that happens between matrices called convolution. And so a convolutional neural network is a type of deep neural network, which just means it has multiple layers, with different layers including convolution, nonlinearity, pooling, and then as well as fully connected layers. So why should a convolutional neural network be used for people detection? Well, one of the most beneficial characteristics of a convolutional neural network is a reduced amount of parameters compared to classic fully connected feed-forward neural networks. As an example, the image here, let's say like we have a raw pixel data as input to the network. That's a 32 by 32 pixel image with a depth of 3. And the depth is referring to the 3 different color channels, red, green, and blue. And so in a fully connected feed-forward network, there are going to be 32 times 3 weight connections between the input layer and then each neuron in the next layer, in the first hidden layer, right? And so if the hidden layer contains, let's just say, the same number of neurons as there are pixels in the image, so like 32 by 32, then that would come out to about, or a little over 3 million connections between the 2 layers, right? But with a convolutional neural network, we can introduce different concepts such as regional connection, which is basically like a kernel of filter. And we can kind of see that in the image here, that small section that's being passed onto the a neuron in the next layer. So using like the concept of regional connections, we could actually reduce the number of parameters quite a bit. Like if we use a 5 by 5 kernel, for instance, and if we still have the hidden layer be like 32 by 32 neurons, then this results in about almost 77,000 connections between the 2 layers, which is quite the improvement from the 3 million that we saw previously. And we could actually reduce this number even further if the kernels, if the weights are like fixed for all of the neurons in the next layer, meaning basically that we could use the same kernel for a single layer, and all like that kernel just passes over the whole image, the same kernel, and then it's passed to the next layer. And that would actually result in, with our case of a 5 by 5 kernel, we'd actually have a total of 75 connections between the 2 layers. So that means in a fully connected feed-forward network, in order to pass all the information from the input layer into the first hidden layer, that'd be 3 million connections. In order to pass all the information from the image using a convolutional neural network, we could actually pass all the information to the next layer with only 75 connections. right? And so that's all talking about the convolutional layer. And then after that, sometimes there's a layer introduced for like nonlinearity. And so that's mainly used to adjust or cut off the generated output. Or in other words, it's used to like saturate the output, right? So maybe like the sigmoid activation function or a hyperbolic tangent, that sort of thing. And we also have the concept of pooling. And so the main idea behind pooling is to downsample in order to reduce the complexity for further layers. Now, downsampling does not preserve the position of the information, so it should only be applied really when information, like the presence of that information, is important, not really where it's located. And then we finally have the concept of the fully connected layer, which would, so with the convolutional layers and pooling, we can think of that as extracting small features from the image, and then it could become more abstract over each subsequent layer by combining these different features and finding more abstract features. But then the fully connected layer would take all of these different features and connect them and produce an output based on all of the different features that has been detected. And, you can go ahead and go to the next slide.
Okay, so what is edge detection? Edge detection is basically like the process of trying to find like patterns or like edges. So in our case, we're trying to detect people. So we'll be looking, we can obviously look for like facial features like eyes, mouth, nose. But then there's also like times where like, let's say we're looking at a person from behind where we can't really use those features. So we kind of have to like look at like the general like outline of a person. So there's basically like two approaches. There's the algorithm approach, and then you can also do the convolution neural network. So the algorithms, basically what they do is they use a kernel. So the Roberts cross uses a 2x2 kernel, and the Pruitt and the Sobel use a 3x3. And a kernel is basically just like a matrix, and it's used to perform the convolution to get the gradient. And so for the Roberts cross, since it's only 2x2, it means that the resulting like image with the edges is basically, it's going to have more noise. And but I guess the benefit to it is that it takes less computation time compared to like the Sobel and the Pruitt, because they use a 3x3. And the difference between them is that the Sobel, you can actually modify the weights, which like it lets you tweak it a little bit more to like adjust like the accuracy basically of like getting the edges. And then so the Canny is another algorithm, but it's actually much more complicated than the others, and it kind of uses them as like a baseline. So like the general idea is that first you use a Gaussian filter to get a blur on the image, and what that does, it basically reduces the resolution of the image. And because of that, it actually like kind of like reduces the noise and makes it easier to like get like the main features of the image. And then the next step is to just apply like one of the simpler algorithms above, like Sobel, which is generally used. And then the third step from there is now you're trying to like thin the edges that were produced from there, because that will make it easier to detect like the basic like shapes and patterns. And then the fourth step is basically called the double threshold. And then you're trying to like find the pixels and like classify them as like strong or weak. And then the strong pixels is what you retain, and then the weaker ones you get rid of. And then there's also like neutral pixels, because they're like in between the thresholds. And then those is like the final step. It's basically like you look at every adjacent pixel to the neutral one, and then if any of them are strong, then you keep the pixel. Okay, so and then in the table you can see that that's like the comparison between using a CNN versus doing the algorithm approach. CNNs are generally like, well, they're more accurate, and they can also use GPUs to speed them up. And you can also like repurpose them. So like if there's like something that detected a dog, you could kind of like repurpose it to detect a person, but you can't really do that with the algorithm approach, because you have to like kind of like do that like by hand basically. So yeah, so the CNNs are generally better, and that's what we'll be talking about a little bit more in the next slides. All right.
So with anything, right, there's always going to be challenges that are going to be faced, right? And people detection is no exception to that. So there's a few different challenges that will arise that might affect the accuracy, scalability, that kind of thing. And so some of these challenges, like we have image clarity issues, so like illumination variation, noise, and then we also have some different challenges for training, such as like generalization, the concept of overfitting, and then scalability. And we'll be talking about these different challenges here momentarily.
So illumination variations are more of an image processing issue where you have differences in illumination on subjects that you're trying to detect. You can see in the bottom, the photo in the bottom right, there's a man's face and there is a light going from one side in front all the way to, I'm guessing, is his left side. That is what illumination variation describes, the differences in lighting on subjects when you're trying to detect them. And a way to approach a possible solution to this is filtering the image properly to extract more features. This is done via convolution, like was previously mentioned. And common ways to manipulate images to increase the detectability of features is either increasing the contrast or sharpness of the image. Contrast increases the difference between high intensity and low intensity values within the image, which can increase detectability of objects. Sharpening refers to, like was previously mentioned, that you want to extract and, I guess, sharpen the edges within an image to make, again, them more detectable. And a common kernel used within convolution for sharpening is the one shown in the bottom left. That is a kernel that, when done via process of convolution applied to an image, can filter it and thus emphasize the edges within the image and increase consistency for edge detection software. So that way, not only can the edges be detected more easily, but in turn, people also can be detected more easily as well. Another common problem found a lot nowadays in images is noise. Noise is a very common issue, and then an example of it, quite an extreme example of noise in the bottom right, you have an image of a woman with a hat, and then the image right next to the woman with the hat is the same image, just with a very high amount of noise. It's an unusual amount of noise, probably not seen so commonly, that amount, but it is an example nonetheless. Like was previously mentioned with Jared talking about edge detection, that blurring is a way to remove noise. And again, this is done through filtering done via convolution. A common filter used through convolution to blur images is a box filter, just a matrix full of ones. When done through process of convolution, that will blur an image, and it basically takes an average of neighborhoods of pixel values and puts them to a single one. Therefore, it can kind of limit noise as a whole. It can kind of average these intensities of these values to make this noise almost disappear. And blurring images is a possible approach to managing noise as well.
Okay, so overfitting, it's basically when the model starts detecting like things that are not related to people in our case. So if there's like multiple images of buildings, then overfitting would be when the model starts to pick up on buildings and use that as in it, and like that's obviously not correct. So what happens is the curve ends up actually going down, as you can see on the right. But the normal, like when it doesn't overfit, it will eventually like converge to like a point for like the accuracy. And obviously like increasing like the number of epochs, that basically I mean, if you do that too much, then you're gonna risk overfitting basically. And then it can also depend on like the optimizer. The two common ones, like Atom will converge earlier, which means that overfitting is like more of a risk compared to SGD, which converges later. And then the solution is to basically so like after each epoch, you wanna run it on or you can run it on like the like random images that weren't in the training data. And then if the accuracy is lower, like after each epoch, then that's when you start realizing that you're overfitting it and then you want to stop the training. But the trade-off to this approach is that it's a slower training time because there's like more like things you have to do. But the benefit is that there's going to be more accuracy. All right, next slide.
So now we're getting into the challenge of scalability. So scalability, this challenge exists not only for like large scale data, but also small scale data, right? So like one challenge is like, how can we better exploit small scale training data to like train a model? And as an example for that, like with object detection in general, you'll have to have several different training examples in order for a network to effectively recognize an object, right? But us as humans, if we're shown like an object once or twice, we can recognize it again, right? We like, let's say even if it's like manipulated later, like let's say a blanket, for instance, like if it's the first time ever seeing a blanket, right? And then you then see it again, but now it's folded up. You could still probably recognize that's a blanket, right? So the challenge exists on how to basically do that with object detection with networks. And then on the other end, we also have the challenge with scalability with like large scale training data. And so for some applications like autonomous cars, for instance, the cost of error is extremely high, right? And in that case, you want the accuracy to be 100%, right? Well, as close as you can get. And one way to like get higher accuracy is to have a large scale like training data set, right? And as long as it's robust enough and kind of like distributed, like overfitting may not be an issue. But the issue is if we increase the amount of training data drastically, then we would hope for a drastic improvement in performance. However, that's not the case. And if we could see here on the graph, it actually is a logarithmic relationship. And so like the x-axis is going to be how many examples we have, and then the y-axis is like the performance metric. And we can see going from 10 million number of examples to 300 million, there's not that big of a difference, right? And so the challenge exists on how to better scale for large scale data. You can go ahead and go to the next slide.
All right, so the conclusion, basically implementing the solutions we discussed is gonna be like the future work for people detection. There's multiple applications like autonomous cars, crosswalk cameras, and security cameras, and these are gonna rely on the technologies we discussed today. Right now, CNNs are basically black boxes, so in the future, like we really want to focus on making them clear box so we know like what's happening in the middle. So I think we're running out of time, so that'll be it for now.
And
And then here's the references.
questions?
More of a statement. I just find it really interesting that when there's a lot of noise in a picture, that the solution is blurring it, because you would think that that would lower the visibility even more, but I just found that a really interesting point.
I do want to add something onto that. In the picture that was provided in the slides, that is a very extreme case of noise where I don't believe blurring would be a perfect solution. There are cases where noise is more light. There are not nearly as many pixels that are changed from the image to produce noise, where blurring would indeed remove the noise. But when you have an extreme example like that was showed in the slide, I can go back to it. Blurring wouldn't necessarily fix it to bring it to how the image is seen on the left, but there are other ways to approach that. Blurring can reduce or remove it if it's not nearly as drastic as that.
I actually I'm gonna send an example in the chat of like a case where blurring may actually like help reduce like the noise. Sorry,
Okay.
I just had to take a screenshot.
Thank you for clarifying.
Mhm.
And I'll take a look at the link whenever you send it.
Any other
we go.
questions?
Yeah, I just got a small question. In your guys' research with all this visualization technology, did you find one particular technology to be the strongest? Because you guys talked about autonomous cars a lot, but is there any particular one that was like that's sat out as the strongest? Or because we talked about autonomous cars having to have very, very low chance of failure. So I just
Yeah, so-
wonder.
Yeah, so we figured out that CNNs are probably like the best, like compared to like the algorithmic approach for like edge detection, and like also compared to like ANNs, which we talked about in class mainly. And the reason for that is because basically, I think, well, I'll let Nick talk about it, but he talked about how you can like reduce the amount of parameters. So if he wants to say more about that.
Yeah, for convolutional neural networks, they are best suited and basically designed for image processing specifically. And so like empirical evidence has shown that like convolutional networks are much better suited for image processing and object recognition, that sort of thing, than other models.
I'm about to say, is the CNN technology easier to implement? Because it sounded like from what it because it was only taking like a smaller portion of like a grand scheme of things from what it looked like. It was just taking like little segments because you were talking about like 3 million for like the normal side, and there was only like 75 points,
Mhm.
I think you said, for the CNN.
Yeah, so it's because with the reason for that is like it's not really like losing information when that's happening, because like in some instances, like if we use a convolutional network on data that wasn't like an image, then information would be lost. But with images, like with the concept of kernels and well, the convolution going over everything, if you break the image into smaller parts, then like these smaller parts are going to build up the entire image itself, right? And so with the concept of convolution going over basically scanning the image, so it's just scanning small parts of the image and then
Piecing it back together.
yeah, piecing it back together. It's figuring out different features that are prevalent in each of these small sections, and then it pieces these small features together in order to into larger, more abstract features.
Gotcha. Like cutting up your food instead of trying to swallow the whole thing.
Yeah.
Gotcha.
That's a good way of putting it.
I got a question. The images, they're accomplished by the use of signals, and the sensors for object detection might be wrong sometimes. Is the settings adjusted, or are the images adjusted? For example, in the blurring slide you guys had, only by the use of filtering?
To my knowledge, filtering it probably is not the only way to process images, but that is one of the most common. I focused mainly on filtering and warping as the main two categories of image processing for our research. So I didn't expand it more into other processes of image processing.
Okay.
But you are right. You are right. Like, sensors can be wrong sometimes, which is why image processing is extremely important when it comes to people detection, because if the sensor is wrong, a person may not be detected, and in very high cost of error situations, that's not good at all.
Yeah,
Thank
and I
you.
think how they do it for like autonomous cars, they use like multiple sensors, so
Mhm.
they can have like a consensus thing where it's like if they all, or like a majority of them detect that a person's not there, that way like it's not just like in case one is faulty, it won't like do anything bad,
Yeah.
Yeah, with high risk situations, redundancy would be a good thing to add. So multiple cameras, multiple sensors.
Very much so. Yeah,
Thank you.
of course. Any other questions?
I think I might have missed it, but did you say that there was a solution to, how the blanket example that you talked about, how if you fold it, a human could realize that it's the same blanket, but did you say that there was a solution to that, or if there's
For scalability, there's not like we didn't cover any solutions for scalability because it's a difficult thing to find a solution for. And like as of right now, like research has shown that like current algorithms are not good at scaling. And
Okay.
so the I guess the solution would be to a different algorithm. But
pop it off pieces and then like figure out those small pieces match, almost like you were talking about a little bit ago?
yeah, and I think in order to like have nice advancement there, we would have to first have like breakthroughs in like the way our minds actually work, right? Like the ability to like implement like common sense, for instance. Like that would be
Yeah.
like, you know, at least I have no idea how thinking like works in us, right? It gives me a headache when I think about it.
Yeah, I was wondering the same thing when you were talking about the blanket example, because we're all in the AI like group thing.
Mhm.
So like if you were trying to like program like a robot, well, like Spot, for example, to go find a blanket, like I was wondering if putting in a different position would make it unable to find it. You know,
Yeah.
like just like you said, like a blanket looks like one thing when it's sitting on the bed, but if it's folded, like would it be able to recognize it as a different object? Because given Spot has more sensors, because like it can touch things, it can feel things like, oh, this is a certain density, if you will.
Yeah.
Maybe you could figure it out, but I don't think you could figure that out purely just by visualization. Or
Yeah.
at least not right now.
And one possible thing for that would be like geometric reasoning. And so like if the network was able to basically see the object in like 3D. So like, I mean, we see in 2D, right? But like we could like move around and see like different angles from the same object, so we can kind of have an understanding of how it looks in like the 3D world. And so if we could implement like geometric reasoning into object recognition, that could improve that, but there's not a lot that's gone into that yet. So yeah, it's all a work in progress, and challenges that's going to be constantly faced for a while at least.
Yeah, I was just kind of interested because I wasn't even thinking about, because we're all talking about like visualization technology because of your slides. And then I was like, I wonder how my camera recognize, or Zoom for that matter, recognize what's me and what's not me.
Yeah.
Because then I was looking, James is on an island, so they figured out what's part of him and then put the rest of them on the island, right?
Yeah.
And I was going like this with my phone, and it got the shape of my body, and anything that's within the distance between the camera and me is visualized, but my phone is not as soon as it goes out. And yeah.
Oh, but it catches your hand too,
Yeah,
and not your.
That's why I was curious, because I was looking at Cameron,
That's
and it
so
looks like he has
cool.
a bun on the back of his head, and it floats in between in and out.
Yeah.
So I was like kind of thinking about it. I'm like, how does it recognize? Because it recognizes my shape quite well. Like it's like a perfect like line, like straight across. And I was kind of curious to how it was doing that.
My guess would be that it's actually using people detection software, and it's like it's specifically recognizing the shape of a person, and then anything that's like near the like the outline of the person, then they probably will not blur or not occlude with different backgrounds. That would be my assumption.
Yeah, because like our cameras, well, as far as I'm aware, don't have like relative distance, so it has to be able to recognize your shape in order to be able to tell what is within the boundaries of what should be shown, and not all my collectibles in the background. So,
and then
yeah, I was just curious.
Size is probably also a thing, because like, I mean, my wall isn't that far away, but if I was in a bigger room and like people were behind me, they'd still have the shape of a person, but I'm pretty sure they would be blurred, or at least I think I've had that happen where people are blurred if they're further away.
Yeah, well, you just put your arm behind your back and blurred that.
Yeah.
So yeah, I was just curious. I was thinking about it when we were talking about it. I'm like, I wonder how that even works. So,
yeah.
But yeah, that was a cool presentation. Thank you.
Yeah, thank you guys.
Cool.
But that's everybody, right? We only had 3 groups.
Yeah, we only had 3 groups.
And he said for everyone to go back to the room, right?
When we were done, I think in order to just verify that we're done.
Okay.
And then to like say bye.
But I think we can actually stop recording though, right, Chris?
I believe we can.
Yeah.
Okay.
Yeah, we've got all the questions through, right? Like we're done completely.
As far as I'm aware.
All right, awesome. I'm gonna stop sharing. and
Yeah.
I'm going to